We just got this video in from the Minnesota Department of Transportation. We want to warn you, this is right before the bridge collapse. Somebody was monitoring the camera, obviously, on the bridge, and you just saw the last car go toward, I guess it would be the left of what you're watching. And you can see the oncoming traffic comes to a stop because they realize that something's wrong.
And then it takes whoever's operating the camera a couple minutes, or at least probably about 30 seconds to realize something is wrong. So then at some point, and you see the cars moving, this is actually, see, this person turned around. The camera starts to move around to go to the other side of this 35W interstate and bridge here, and there's a Mississippi, and there you go.
And you can actually see people jumping out of their cars, running to the side, some people stopping to see what's going on, but then you also see a number of people jumping out of the car, running away, and even turning their cars around and driving away from the scene.
We have been helped out by some digital surveillance video, though, that was taken from the Lock and Dam, the Army Corps of Engineers, releasing this video to the media today, as well as the authorities with the NTSB. They have used it to try and determine what happened. Mayor R.T. Rybak has told us that they were hoping to see more from this video. They were able to see some things that they had their doubts about, some things that may have answered some questions, but not as much as they had hoped to see. But this is just a piece of the puzzle that they'll be going over in the next several days, weeks, and perhaps months ahead. But it will help speed up the investigation process.
At 6:05 p.m. August 1st, 2007, disaster struck. In less than a minute, the I-35W bridge spanning the Mississippi River in Minneapolis, Minnesota, was reduced to rubble, claiming the lives of 13 people. Soon after the collapse, people across the nation were asking, why did this happen? How can a bridge that had stood for 40 years simply collapse in a country with as many resources as the United States? Completed in 1967 by Industrial Construction Company and Huracan Incorporated, from designs by Svendrup and Parcel, the I-35W bridge was, in its entirety, over 1,900 feet long. It consisted of 14 spans, 5 south approach spans, 3 main spans, and 6 north approach spans. The 3 main spans were of deck truss construction, where structural steel beams supported an upper roadway deck, while all but 2 of the approach spans were multi-girder steel construction, concrete supported by several I-beams. The final 2 approach spans were of simple concrete slab construction. The center span of the bridge consisted of a single 458-foot steel arch truss with 2 support piers located on the north and south riverbanks. Each support pier had 2 load-bearing concrete pylons at either side, capped with roller bearings. These allowed the bridge some flexibility due to changing weather and traffic conditions. The center span rested on these bearings and was connected to the north and south approaches by shorter spans formed by the same main trusses. Both spans were 266 feet in length and were connected to the approach spans by a 38-foot cantilever. The truss system consisted of the main trusses, the transverse deck beams, deck stringers, and finally the reinforced concrete roadway deck itself. The deck was 113 feet wide, divided in the center, and had expansion joints at the centers and ends of each of the 3 main spans, again to allow for flexibility to environmental changes. At its highest point, the roadway deck was approximately 115 feet above the river. One final note on the design of the I-35W bridge is that it was designed in an era when redundancy was still not widespread. This meant that if any one system failed, it could bring down the entire bridge. While an ongoing investigation is still searching for the actual cause or causes of the bridge collapse, there's a great deal of information on the state of the bridge prior to the collapse and potential contributing factors. As early as 1990, the bridge was rated as structurally deficient by the U.S. Department of Transportation due to corrosion on the roller bearings. By 2004, this corrosion would almost completely freeze the bearings, forcing them to release built-up stress in sudden jolts. In 1993, inspections were increased from biannually to annually, as corrosion was found in the steel forming some of the bridge joints, and fatigue cracks were discovered in the bridge approach spans. Cracks were treated by drilling holes at the ends to prevent them from spreading. An independent study in 2001 by University of Minnesota engineers again deemed the bridge structurally deficient, but not in need of immediate replacement. Their research showed that the fatigue cracking of the deck truss had not occurred and was not likely. However, they had noted many poor fatigue details on the main truss system. The most recent study, conducted by the consulting firm URS in 2006, recommended that 52 beams be reinforced by bolting on additional steel plates, only to state in a January 2007 supplement that the drilling required to install the plates would significantly weaken the bridge. They suggested further inspections, but echoed many previous inspectors in saying that visual inspection would miss as much as 90% of fatigue cracks due to access issues and debris such as bird droppings. Repairs were ongoing at the time of the collapse, with Progressive Contractors Incorporated resurfacing 4 of the bridge's 8 lanes. The concrete resurfacing was not considered structural in nature, as ordinarily only 2 inches of the 9-inch concrete slab are replaced. However, some areas of the bridge required complete replacement, leaving open gaps in the road deck. If one of these gaps was over an undiscovered fatigue crack, it would place a great deal of stress on that point. The added weight from construction materials and equipment focused on the area could lead to deck failure and, potentially, a catastrophic collapse. Whatever the ultimate cause or causes may be, Information gathered from the collapse will be used to educate architects, engineers, and politicians to help prevent further disasters.